This is AP Calculus BC, and in this video, I'm going to talk about section 10.2 polar coordinates. So what this section primarily is going to be is mostly it's a review of things that you saw last year in pre-cal as it pertains to polar coordinates last year or the year before, depending on your sequence of courses. When we start working in polar coordinates, there's a couple of reasons that we would do this. So number one, sometimes we have situations where it is more easily modeled in cycles. And so polar coordinates, it's very easy to model a function that operates from the perspective of a cycle. And in addition to that, when we start looking at things in 3 dimensions, sometimes we're going to want to use what's called cylindrical coordinates. And cylindrical coordinates are a 3 dimensional version of polar coordinates. Now, also sometimes with the curves that we see in polar coordinates, you'll see that they're not actual functions as we see them in the Cartesian system. But from a polar perspective, they're very easy to deal with. Whereas if we had them in a function situation or a Cartesian situation, it'd be very, very hard to deal with. So a couple of things, just quick reminders. Remember when you graph, you're going to use the coordinate r theta, where r is the distance from the pole, theta is the angle measured off the positive x-axis. We have the relationship between the Cartesian coordinates and our polar coordinates. X is r cosine theta, y is r sine theta. We also have r squared is x squared plus y squared. And then we have the simple trig representation, tangent theta is y over x. So I've got a graph here. This is just the polar coordinate plane. So remember when we graph a point in the polar system, we first locate the angle, the theta value, and then we go out to that angle some r distance. So for example, if I'm looking at the point 2 pi over 3, the way that I'm going to graph that is I'm going to say, okay, out to here is the pi over 3 angle. And then if I want to go 2 units from the pole, that would put me at that point, and this would be 2 pi over 3. Okay, so again, graphing in this system is a little different because we have to be thinking about a rotation around the pole, which we normally in the Cartesian system would have called the origin. Okay, so let's talk a little bit about going back and forth between the two coordinate systems. If I want to write a polar point in a rectangular coordinate system, all I have to do is remember the relationships. X is equal to r cosine theta, and y is equal to r sine theta. Okay, so here they gave us the point 2 pi over 3, which is the point I plotted just a second ago. And what they're asking us to do is they're asking us to convert that to its rectangular coordinates. So since I have the point 2 pi over 3, that means r value is 2, and the theta value is pi over 3. And when I simplify that out, that's going to be give me an x coordinate of 1. And then for the y value here, I've got r as 2, and then sine of pi over 3. And that's going to end up giving me root 3 over 2 times 2, or square root of 3. Square root of 3. So that would be my coordinate in the rectangular coordinate system or the Cartesian coordinate system. So 2 different ways of referencing the same point. Okay, so now let's look at converting the other way. So here it says represent the point with the Cartesian coordinates 1, -1, and we want to convert that into polar coordinates. So there's a couple of things that we have to remember here. We have to remember that r squared is x squared plus y squared. Well, from that, I know that my r squared is essentially 1 squared plus -1 squared. So my r squared value is 2. That means my r is the square root of 2. And the other relationship we had was the fact that tangent theta is equal to y over x. So in this case, that means tangent theta is going to be equal to -1. So that means my theta value would be negative pi over 4. And I'm always going to use these theta values when I do an inverse tangent. I'm always going to go from negative pi over 2 to pi over 2 because I want to be as close to 0 as possible when I'm measuring those theta angles. Okay, so in the end, what we have then for our coordinate would be square root of 2 negative pi over 4. Now, one of the tricky things about polar coordinates is that I can represent a coordinate in my polar plane in an infinite number of ways. So I mentioned when I did an inverse tangent, I always want to choose the theta value closest to zero. But once I get beyond that and I'm just looking at a coordinate, I can reference that theta angle in any equivalent way. So for example, I could have gone, instead of going in the negative theta direction, I could have gone in the positive theta direction and said this was square root of 2, 7 pi over 4. Or I could have gone in a negative r direction, which is kind of strange to think about. But normally, whenever we reference one of those theta angles, we measure out away from the pole in the direction of that angle. Well, we can also go opposite. So, for example, I could do negative square root of 2, 3 pi over 4. 3 pi over 4 is an angle that points in the opposite direction away from the pole. But if I go negative from an r perspective, that's going to put me at the same point. So any one of these coordinates in the polar coordinate system has an infinite number of equivalent representations. Okay, so let's talk about graphing in polar coordinates. So again, this is just a reminder. So when we graph in the polar coordinate system, we're always going to have r as a function of theta. The first graph that we have here is just r is equal to 2. So hopefully you recognize that as a circle, because what that means is regardless of what my theta value is, my r value is always going to be 2. So in the end, I'm just going to end up with a circle with a radius of 2. Now, I have a second one here that's r is 1 plus sine theta. There's a couple of ways that you can graph these things. But really, primarily, we're going to do this on the calculator. I'm not going to ask you to do a bunch of r theta tables and plot points. What I really want you to do is plot something like this on the calculator. So that's what I want to show you here. Okay, so just a reminder in terms of graphing in the polar coordinate system on your calculator. Remember, you've got to change the mode of your calculator, and you're going to want to put it into polar mode. So I switched the mode on the calculator by hitting the mode button. I switched to polar. And now when I hit y equals, I'm going to have an r equals equation there instead of a y equals like we would have in a Cartesian system, or x equals and y equals for a parametric system. So I'm going to put in the equation that we were just looking at, 1 plus sine theta. And then you always want to think about your window settings for these. So my theta values, I'm typically going to want to go from 0 to 2 pi, but it depends on the situation. What I want to try to do is at least graph enough that I see one full cycle of my graph. The theta step is just the distance that you're going to step in the theta direction to get the next point. So your calculator is not actually graphing r equals 1 plus sine theta. What it's doing is it's finding the r value for the corresponding theta value, and it's just doing a bunch of points and connecting them together. So if we make this theta step relatively small, like 0.1, which was pretty much what it was defaulted to, that's going to give me a good view of what this looks like. If you make your theta step too big, you'll start to see that you'll see kind of linear sections pieced together, and it won't look like a smooth curve. Okay, so now I'm going to graph this. And you can see I've got this shape here. And I'm actually, typically when I graph in a polar mode or a parametric mode, I usually do a zoom square so I can get a good feel for what it looks like. So this is the graph that I have. And there's names for all of these. That's not something that I'm asking you to remember. I know in pre-cal sometimes you go through the names of the polar curves. That's not something you really need to know how to do. What I need you to know is how to graph them, especially on the calculator, and how to interpret the graphs. And that will allow us to get into some applications. Some other things that we were looking at here, the idea of symmetry. So we can actually use symmetry when we're graphing in polar coordinates. There's symmetry about the x-axis, about the y-axis, and about the origin. And we can do different things with our theta values to see that symmetry. So essentially what it is kind of a test. If I can replace, you can see in this first part A here, if I can replace theta with negative theta, that means I have symmetry about the x-axis. So this is what I'm looking at right here. For symmetry about the y-axis, if I can replace theta with pi minus theta and I get an equivalent equation or an equivalent point, that means I've got symmetry about the y-axis. And then if I want symmetry about the origin, I want to go, I want to shift pi units away from that. And if those are equivalent, then I'm going to have symmetry about the origin. Or if I can replace r by negative r, and that gives me an equivalent graph, then I've got symmetry about the origin. Now, those are not things you need to memorize, but they're little things that can be helpful from time to time when we start working on integrals involving polar coordinates. Okay, we've also got some of these symmetry properties just plotted here to give you a view of how they would work. And I'm not going to go through that. You can read through those on your own just to get a feel for how that would work. So the last part of this is really the most important part because this is where we start to get into the calculus of dealing with polar curves. Now, the nice thing is this is very much like what we did with parametric equations. So when we are looking for dy dx, the slope of our curve, what you have to remember is x is r cosine theta and y is r sine theta. And so you can see I have this thing that looks like a gigantic mess here to represent dy dx. That's not how I do these types of problems. So when I'm looking for a dy dx from a polar curve, the main thing that I have to remember is this part. It's dy d theta divided by dx d theta. So as long as I know that y is r sine theta, I can take the derivative of that y with respect to theta, and then x is r cosine theta. I can take the derivative of the x with respect to theta, and then just divide, and that gives me dy dx. So if you want to, sure, you can remember this, but I don't really think it's worth your time when it makes a lot more sense to just remember conceptually what we're actually doing. We're doing dy dx, and to get our rates of change, we just do the y and the x independent of one another. Okay, so from a horizontal and vertical tangent standpoint, this again is just like what we did with parametric equations. So I want to remember if I'm looking for a horizontal tangent, I need that slope to be 0. So when I'm looking for a horizontal tangent, the numerator has to be 0 when the denominator is not, because that would give me, for instance, 0 divided by 5, which is equal to 0. But if I get 0 over 0, well, that's going to indicate that I have a special type of point, which is typically going to be a cusp in my curve when I have a 0 over 0 or an indeterminate form. When I look for a vertical tangent, I want the denominator in this expression to be 0 when the numerator is not. So for example, 5 divided by 0 would give me an infinite slope or a vertical tangent. So again, we want to make sure that dy d theta is not 0 at the same time. Okay, so the last part of this, if we want to find tangent lines at the pole, so that means r is equal to 0, then we can just say dy dx is equal to tangent theta. So if you think about that, it kind of makes sense because if we take the r value out of the whole thing, if x is r cosine theta, y is r sine theta. If I do my y divided by my x, all of the r parts are going to cancel out when I take the derivatives. And so this stuff goes away, and you can see this stuff goes away. And what I end up with is sine theta over cosine theta, which is tangent theta. So that's kind of a special case. But most of this stuff, if you understand that it's dy d theta over dx d theta, all the rest of those things you don't really have to memorize. They kind of take care of themselves. Okay, so I've got one example here that I wanted to work through with you. It says for the cardioid, r is 1 plus sine theta. And it says of example 7 because I got this from a book. This is actually the graph that we did earlier. It's called a cardioid. It says find the slope of the tangent line when theta is pi over 3. Okay, and then on the second part of this, find the points on the cardioid where the tangent line is horizontal or vertical. All right, so let's look at part A first of all. And what I'm going to do here is I'm just going to go through these calculations with you. So for part A, if I'm going to find the equation, the slope of my tangent line, I need to know what dy dx is. So remember, dy dx is the same as dy d theta divided by dx d theta. And if you understood this when we went through parametric equations, this is going to seem really simple because I know x is r cosine theta. So my x in this case, if I plug in my r was 1 plus sine theta, and I'm just going to multiply that to cosine theta, I would end up with cosine theta plus sine theta cosine theta. Okay, so just to be really clear, what I did there is I took this expression and I plugged it in for r. Okay, so make sure that that makes sense to you. Then we can do the same thing for the y. We have r is, or y is r sine theta. I'm going to take that r equation, I'm going to plug it in, and I'm going to end up with a y equation of sine theta plus sine squared theta. All right, so now from here, I want to get my dy dx. So remember, dy dx is just going to be dy d theta divided by dx d theta. So I've got to do some derivatives here, but here's my x equation right here. I'm going to take the derivative of that with respect to theta. And when I do that, what I'm going to end up with, or excuse me, I want the y equation. I want to take the derivative of this with respect to theta. And when I do that, I'm going to get cosine theta plus 2 sine theta cosine, or let's see, 2 sine theta times cosine theta when I do my chain rule. Okay, and then for the denominator, now I'm going to look at the x equation because I want dx d theta, and the derivative of cosine theta plus sine theta cosine theta. Derivative of cosine is negative sine, and then the derivative of sine theta cosine theta is going to give me, let's see, I'm going to get cosine squared theta minus sine squared theta. And so the last piece of this, if I want dy dx at theta equals pi over 3, I've got to do some work here because I've got to know my unit circle values, but I would plug in pi over 3 in for all those thetas, and you find that the slope at that point is -1. Now I have the graph of this figure down below, so you could take a look at it, and you can see that when we're at theta is equal to pi over 3, you can see we have this slope of -1. So you can always get your results and kind of compare to what your graph looks like. And obviously this says it's -1, but even if I didn't have that labeled there, I can see that a slope of -1 looks reasonable. Okay, so we could do that with the slopes at any points. Now let's do the same thing for part B. And I know you just saw the answers for part B, but I want to show where they came from. Okay, so for the second part, we're trying to find horizontal and vertical tangents. So remember, if I want horizontal tangent, I'm looking where is dy d theta equal to 0. And that means my dy d theta was cosine theta plus 2 sine theta cosine theta. I want to know where is that equation equal to 0. And that trig equation is something you should know how to solve from your pre-cal days, but we could factor a cosine out and then set both parts equal to 0. In the end, what we would end up with here is theta is equal to pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. So I've got 4 potential horizontal tangents. Now, I'm not sure these are horizontal tangents yet because I have to know where dx d theta is 0. So I've got to check both of these. Setting dx d theta equal to 0 is going to give me potential vertical tangents. So for dx d theta set equal to 0, we have negative sine theta plus cosine squared theta minus sine squared theta set equal to 0. So for this one, it's a little more complicated, but I can convert that cosine squared to a 1 minus sine squared, and then you can do some factoring and solve this one out. In the end, what you'll end up with here is theta being equal to pi over 6, 5 pi over 6, and 3 pi over 2. Okay, now we want to check, do they share any of these values? And the value that they share is the 3 pi over 2. So what that's telling me is I've got something special happening at that point because my slope at that point is 0 over 0 or an indeterminate form. But what I also know is I now know where my horizontal and my vertical tangents are. So for the horizontal, they're going to occur at the points where theta is equal to pi over 2, and then also 7 pi over 6 and 11 pi over 6. And then for the vertical tangents, that's going to occur at theta is equal to 5 pi over 6 and pi over 6. Okay, so those are all of my values then. And those are the points where I've got horizontal and vertical tangents. And now we can just verify those on the graph. You can see for the horizontal, we said pi over 2, which is here. We've got a horizontal tangent at 7 pi over 6, which is here, and at 11 pi over 6. Those are all horizontal tangents. And then for the vertical tangents, we had pi over 6 and also 5 pi over 6. Okay, so algebraically solving these out, there's a little bit of trig involved. When you get the algebra worked out, you've got to know some trig identities, and you've also got to be able to use those unit circle values. But remember, big picture, the main idea behind this is always centered around this relationship. If you know that relationship, the rest of this stuff is intuitive, because you know a horizontal tangent line means that you've got a zero slope. You know a vertical tangent line means you've got an undefined slope. Okay, so that should be everything that you need for the 10.2 assignment. What we're going to do next time in 10.3 is we're going to start to get into a lot more of the calculus when working with parametric equations. Now, what I also included in this packet that I want you to take a look at is I did put in a sample AP free response question on parametric equations. We're not quite ready for one on polar equations yet, but I wanted to show you this one on parametric. So make sure you read through that and look at the scoring guidelines. We'll talk about this a little bit in class, but this starts to give you a feel for the types of questions that you might see on your AP exam as it pertains to the topics that we're covering in this last unit. Okay, and one last thing here. I did include a worksheet at the very end of this packet. If you feel like you need some extra practice on some of the basics of polar equations, I did put this worksheet here. I think this would probably be more useful in preparation for your test, but it is something that you can use at any point. You've got the worksheet here, and then you've got the corresponding solutions there. So I would save it until right before the test, and you can use it for extra practice. But if you feel like after the assignment in Wiley Plus that you still need more practice, you can always go to this worksheet and get some more practice problems.